Hi, I'm Bernd, and I want to welcome you to a basic training on wastewater testing for ZDHC and detox. This is one of the key elements for our sustainability service. I hope you'll find some interesting information here. We'll break down things as follows. First, we start with the background to understand where the requirements originate from. Then, we move on to basics to cover some general principles of analytical chemistry. Sample preparation is next, followed by analytical techniques as we apply them in the laboratory. Last but not least, also quality should be looked at. Things started in 2011 when Greenpeace launched this detox campaign with a dirty laundry report. This was followed up by some of the brands which were targeted, such as Adidas and Nike, by forming ZDHC. This organization then released in 2014 the first document, the MRSL, which sets limits for chemicals in formulations. The first Wastewater Guideline followed very soon in 2016, and that also needed the involvement of labs like ours. This was achieved by forming the Lab Advisory Group, counseling the labs for technical advice. What followed was then an expansion, and soon sludge testing was included into a new version. Finally, this year, 2022, the 2.0 version of the Wastewater Guideline was released. Here are some further resources if you'd like to dig deeper. On one hand, the ZDHC Wastewater Guidelines, which is the main document, as well as the supplementary document, which is the sampling and analysis plan. Also from ZDHC released on the Academy several webinars with more information on various topics from ZDHC as well as clarifications. On our side, in-house, we have the Detox SharePoint, which is very well maintained and contains a lot of information from the colleagues. The Wastewater Guideline can be looked at from two angles. On one hand, the parameter groups, so the chemicals that we analyze, those can be structured in three different groups: the conventional parameters, metals, as well as the large group of MRSL parameters, which originates from the MRSL list that ZDHC published for chemical formulations. The second group refers to the matrix, means the material we analyze. This could be either the classical way, wastewater or sludge, or, and this is new, the leachate of the sludge. Let's have a look at the other high-level changes in the version 2. For example, the inclusion of leather requirements. MMCF, man-made cellulosic fiber requirements, however, were not incorporated in this version. The MRSL version 2 parameters have been added. Small facilities with a discharge of less than 15 cubic meter per day are subject to only very light testing requirements. Then there has been an update of conventional parameters with exchange or inclusion of additional parameters. Sludge disposal pathways have been defined, and there has been the introduction of the wastewater candidate list to give an outlook what to expect for the version 2.1 or possibly 3.0. Now we just saw the high-level changes. When we take a closer look, like here, you will see that almost no stone has been left unturned, and everything that is red here has been a change. So most of the parameters have gone through some change, either with the required limit, the test method, or the scope of parameters. Consultation period was very short, and there have been a few known issues identified in this requirement. For example, the E. coli method needs to be updated. PFAS list and limits are missing or not aligned with previous versions. Cyanide in leachate requires some review regarding the recovery rate and also the safe handling of the samples, and also leather limits have been missing here. In this chapter, we'll cover some basics of chemical testing. What is the origin of analytical chemistry? While it's difficult to define an exact starting point, what we know is that around 2300 BC there was a dry analysis to define the purity of gold. This is a cupellation procedure which is still in use in a similar method today. Pigments were another precious commodity. And 2000 years later around, we know about copper sulfate analysis in copper acetate, which is already a more targeted approach. We then enter the age of the alchemists, and we found some very precise numbers for the determination of density of different media. You see it here in the table above. Later on, Paracelsus, the early toxicologist, also analyzed water and had consumer protection on mind to determine if water is potable or not. After a while, we entered into the more modern chemical analysis, among others with Bunsen, who was the father of spectral analysis, which is still in use nowadays in many of our spectrometers. In the end, it became more and more important and to see that analytical chemistry is essential for other sciences like medicine, pharma, forensics, geology, you name it. So everywhere we need to analyze what we have on hand in order to make further progress. Then in the 1970s around, this is where the modern trace analysis started with technologies like chromatography, other non-destructive analysis, and also the instrumental analysis developed to the point where we are today. Let us now get an impression of the scale at which we are analyzing. You see here the gray cube is an expression of one unit as a whole. 1%, as you see here, this part is a rather sizable chunk which is easy to visualize. Common is for us to analyze at a level of 1 ppm. You see here, which is only a tiny dot of the whole cube. So this is already a very, very small fraction. However, that's just where it starts when we talk about wastewater testing. There we commonly go down to part per billion, which, if you want to imagine this one, would be representative of 3 seconds in a whole century. For some parameters we even have to get lower than this, talking about part per trillion. To imagine this, think about not 1 but 20 Olympic-sized swimming pools. Then add 1 drop of water and try to find it and determine its presence in the big water body. Here's some example to illustrate in which range we analyze when we talk about wastewater. An example from the Wastewater Guideline 1.1. Here is for PFC we go down to a level of 10 ppt, while for COD, marking more the upper range, we are determining levels of 150 ppm. In the following, let's have a look at sample preparation. Once the sample arrives at the laboratory, we will have to do some homogenization in order to make sure that the sample and the analyte is distributed homogeneously. Then we also may have to do further division, for example of sludge or soil samples, and also those need to be representative. Another stage frequently used for mechanical or physical sample preparation is drying in an oven, among others to determine the dry residue or to process the sample for the next steps. It would be nice and practical if our sample would be only made up of water and our analyte. Unfortunately, this is not the case. Wastewater has quite a lot of constituents. Some are demonstrated here. So we will have accompanying materials, often these are solids or salts, other interfering substances that can also have an influence, a negative influence on our analysis, such as surfactants or isomers of actual analytes. And the actual substance we are interested in, the pH. So everything that is not our analyte, we call it a matrix. In order to obtain results at the very low levels we saw in the previous slides, we will have to clean this up. This often needs a separation to separate our substance of interest from everything we don't want to see in the analysis. So we have to start with more steps in order to process the sample. One way to process a sample is the so-called liquid extraction. It's a basic technique and especially helpful for wastewater analysis. So what you see here in the first step, we fill our sample into a separation funnel. This sample contains, as we saw, our analyte, here the black round dots, and the blue matrix, everything else. What we do in the next step is we add solvent on top of it. Typically, this is an organic solvent, so the phases separate. So you see here our organic solvent on top and the water sample with our analyte on the bottom. Then we shake and mix the layers vigorously. This can be over a minute, couple of minutes, half an hour, depending on how we process the sample and how similar the solvents are. Then we will have a distribution. Most of our analytes will move into the organic solvent phase. A few will remain in the wastewater phase, but this is not a problem. We can determine this by carrying an internal standard with us. With this kind of setup, we usually get a relatively clean organic solvent layer with our analyte and can leave a lot of the dirt and unwanted substances in the water phase. The beauty of this procedure is also that we can work with a relatively large water volume and a small solvent volume. Means we will not only achieve a kind of cleanup, but we will also add a concentration step in the same procedure. Another example of a common sample preparation technique is the solid phase extraction, or SPE. For this, we use ready-made cartridges, which can be purchased from suppliers, and in the first step we condition them, for example with methanol. In the second step, we load the cartridge with our wastewater sample you see here in step number 2. Some of our analyte, but also some unwanted substances, will absorb to the bed of the cartridge. In the next step, we can wash it and therefore rinse off unwanted substances and matrix we don't need. Finally, in the fourth step, we use another stronger solvent and remove our analyte from the cartridge. Same as we saw before for the liquid-liquid extraction. Also here we have the chance to use a relatively large sample volume for loading in step 2 and a small volume for the elution in step number 4. We just saw 2 examples of extraction. Another step may be necessary, for example a derivatization. This could be used to make a non-volatile compound volatile, so it is accessible for analysis by GCMS. Other groups could be added as well, for example a chromophore, in order to give the molecule the property to absorb light at a certain wavelength and make it accessible to spectrometric methods. Examples of making a non-volatile compound volatile is derivatization of organotin compounds. Other steps can also be added, for example additional concentration steps, as you see it here with a rotary evaporator, in order to reduce the solvent volume and therefore relatively increase the amount of analyte. In chapter 4 we will have a look how we analyze the compounds after we've done the sample pretreatment. First we have a look at a very widely used technique. This is photometry. We basically use a light source, filter out a certain wavelength of the light emitted, pass it through our sample solution, and then register the absorption that our analyte causes in this solution. Based on the absorption we can draw a calibration graph and therefore determine the content of our analyte. ICP-OES is a technique for determination of heavy metals. This uses the principle of emission, means light is emitted from our analyte when it's subjected to very high energies, like in this case plasma. Here we reach temperatures which are similar to the temperatures on the surface of the sun, that is around 7000 degrees. While there is energy emitted from our analyte in this environment, we can detect both the wavelength emitted, which gives indication of what element we are analyzing, and also the signal, which gives an indication of the concentration of the element in our solution. Let's now have a look at chromatography, another very important technique, especially for organic analysis. As we saw previously, our sample contains a lot of different components, and we have to separate them in order to identify them. Chromatography is one way to do this. You see this here in a simple example that you may even be able to repeat at home, and maybe you have seen it with inks, for example. So here we see that we have a kind of a cardboard in a solvent within a glass cylinder which has a saturated gas phase. Here we can now start, if we let the solvent run up the plate by capillary effect, it will carry with it our ink and all the different components in it, and it will separate them over time. And because it was so nice, let's look at it one more time. So what happens here, and why do we have this kind of separation? We can imagine this in simple ways, like a family that walks through a shopping mall, starting from the entrance and agreeing to meet up at the ice cream shop. So the family consists of mother, father, daughter and 2 young kids. So they will start out, and if the shopping mall consists mainly of fashion shops, you will probably have the kids run through, quite uninterested of all the shops, to the ice cream shop and arrive there first. The father, also not that interested in fashion, will probably arrive second. The daughter, she will take it a bit longer. She will browse around, probably hasn't the funds to spend much money, so arriving third. The last one to arrive, we expect, and sorry for all the stereotypes here, is probably the mother. She's interested in fashion, she has money to spend, so her dwell time in the mall is the latest, and she will arrive last. How do we translate this to our world of molecules? Well, we have different kind of molecules. In simple terms, polar ones and non-polar ones. We can now choose our stationary phase of a separation column that represents our shops in the shopping mall here to be either polar or non-polar. So let's assume we have a non-polar separation column and non-polar molecules. So they will stick the most to our separation column, and the more time they spend there, the later they will get off the column. So polar molecules will come out first at the end, non-polar molecules will come out last. So in this way we achieve this kind of separation also with chemical molecules. This separation gives us important information about the molecule. It gives us the so-called retention time, means the time at what the molecule leaves the column in comparison to other molecules. This still doesn't give us a real identification of the molecule though. So what can be done, for example, is a mass spectrometric method. There we shoot an electron beam onto the molecule and break it apart. We ionize it and then detect the different fragments of it. 2 examples here, a more stable one on the left hand side and a less stable one on the right hand side. So on the left hand side we see it doesn't break down into many fragments. On the right hand side, however, we get a lot of small fragments, as you see on the shift of the different masses to the left hand side. This kind of unique pattern gives us important information, the so-called mass spectrum. With this we can go into a library or compare it to standards that we have run earlier and get a real identification of our molecule. Also, in addition, if we look at the peak area, we can get an idea about the quantity of the molecule in our sample. We now had a look at a few selected techniques. There are a lot more in the chemical lab and a lot of variations between them. But we will conclude it here and next on have a look at quality. When it comes to the quality of test result, it's important to understand that the first steps in the process are especially important. In our case, this is the sampling. So it seems a bit contradictory that the process which is carried out with the least sophisticated and probably the least expensive equipment is the most crucial in this step. But fact is that errors we make during sampling cannot be in any way bettered during the rest of the process, which includes sample preparation and the actual measurement. For example, if the wrong preservation is used for the storage of the sample, or the temperatures are wrong and our analyte decomposes during storage, we will not be able to find anything in the following steps. Therefore, in simple terms, we can also say garbage in, garbage out. As part of the sampling and analysis plan, ZDHC has set certain requirements for quality control. These include, for example, to prepare a field blank, method blank, calibration check, lab duplicates, internal standards or surrogates for samples. Dedicated requirements are stated in the document and can be found on the ZDHC website. Some of these requirements are a bit different from what we know from product analysis, so it's important to have a look at this and understand the requirements. Another part in the ZDHC framework is the lab acceptance. Only laboratories accepted by ZDHC and formally published on their website are permitted to perform testing for the Wastewater Guideline. Some of the criteria are listed out here in the table below, and you can see that not everything has to be accredited, but in other cases we can also provide validation data, for example, as well as additional documentation. To go through the lab acceptance process, ZDHC has set up the Lab and Certifier platform. This is an online platform where all documents can be uploaded electronically, and also the communication to achieve final agreement on everything is going online through this platform. Several of our labs have already completed this step. They are now successfully offering services to our clients to help them become a green and sustainable textile producer. I can just encourage every one of you to give it a try and to join the team. Should you have any questions, please feel free to reach out to me or to any of our wastewater labs. So, good luck, good success, and thank you for joining the training.